Well, hello. Welcome back. Nick the Vic here, M0NTV. And yeah, welcome back to my shack. And Happy New Year to you. And apologies, I'm a bit overdressed for the occasion, really, but I'm kind of in the middle of something. Yeah, but I wanted to do a video. The first video of the new year is going to be about one of the most important parts of a single sideband transceiver, which is the mixer. And so what I'm going to build is a diode ring double balanced mixer. Now sometimes people ask, well, why would you bother? Why don't you just buy one? And yes, of course you can do that. And I've used ADE ones and SBL ones and yeah, you can do that. But I suppose the answer to that question is, why would I build it? Because I can, yeah, because I want to, because I want to understand how it works, and that really kind of cuts the whole heart of the homebrew question, isn't it? Really, I don't need to build a transceiver. I could save up and just go out and buy one, but I do it because I'm interested in how it works. So that's what we're going to do. We're going to build a double balanced diode ring mixer, and actually, this video is really kind of going to be a part of a three-part mini-series, really, because there's such a lot of material around this, and I don't want to make one ridiculously long video that hacks everybody off. So I'm going to kind of split it up a little bit. Yeah, so without any further ado, let's have a look at the schematic. And it's very simple. As you can see, at the heart of it is this diode ring bridge. So four Schottky diodes, they're connected in a bridge formation. I'm not going to go into great details about how this actually works. There's plenty of information available and people that can express that in far better ways than I can. But essentially what's happening is, as I understand it, on the positive excursion of your wave, two of those diodes are biased on and are conducting and two are off, and then on the negative excursion of your wave, the opposite, the other two diodes are biased on and the other two are off. And it's not a linear process, which is good, because what that means is we get our mixing process. That is to say, we put a signal in on the left there at the local oscillator port, and then we either put a signal in at the RF port and take the output at the IF port, or we put a signal in at the IF port and we take the output at the RF. It's up to you how you do it. And what you will then get at whichever your output port is the sum and the difference frequencies. And this, of course, is the backbone of the whole super heterodyne method. Yeah, so really important. And we'll go into detail of how we're going to build it and how we're going to make it right now. Well, welcome back to the bench, and we're going to build a double balanced diode ring mixer. And essentially, there's only really two bits to this. There's the diode ring in the middle, and then there's the trifilar wound transformer on either side. So we're going to come back to the diode ring, but we want to just have a look first of all at building the transformer. One of the transformers and the other one will be identical. So now this calls for, I've got down the bottom there, 10 turns trifilar. I use number 28 gauge wire on an FT3743 toroid. So here's the toroids. So tiny little things, really, aren't they? 10 turns is about all you're going to get, to be honest, on one of those, because this is trifilar. So it's three wires twisted together and wound as one then on the actual toroid. So what I'm going to use to kind of help this
is, first of all, I've got some bifilar, two windings from the good old GQRP club. So this is a green and red, which is really helpful because it really helps with the phasing of this, because you can tell which wire is which. And I'm supplementing that, and this is slightly lighter, it's 28 gauge, but that's fine. Enamelled copper wire, so it's just one. And what I'm going to do now is to actually take a length of this and the length of that and twist them together, and that will form the basis of our trifilar winding, and I'll show you that in just a sec. So I've just taken off about 30 centimetres length of this bifilar wire, the green and the red, and slightly more, about a couple of centimetres more on the gold single one. We're just going to keep that as a longer leg just for identification purposes, really, more than anything else, because that's the totally separate winding. There'll be no electrical connection between the gold and the other two. And what I've done on the bifilar piece, I've just gone over with a Stanley knife there and just separated those two wires at the end, and you'll see why in just a second. Now what I've done is I've now gathered together the bifilar wire and the single wire, and this end here I'm going to put in the vise, slightly splayed out as you can see there, so I can get a good purchase on it. And then I'm going to attach to the other end a clip. I mean, you can use whatever you've got. I'll show you the clip in just a moment. Okay, so you can probably just about see I've got the 3 wires now in the vise. You can see the red one sticking up there. And in a minute I'm going to pull this taut, but the other end is attached to this clamp here. And I've splayed those ends out as well, so I've got a good purchase on that end. And all I'm going to do in just a moment is this. I'm just going to take this out. I'm going to hold it straight like this, and I'm just going to rotate it clockwise and keep doing that until I've got lots of little turns on, and I'll show you what that looks like. And here we have it. Now I'll just try and get in there a bit closer and show you what I mean. Now it actually looks quite cool, because what you actually get it's like these little colourful beads where the turns go, and you can see that regular pattern going, which is what you want, because you want the inductance to be as even as possible across the whole the turnings. Now there's a kink there in the wire, and yeah, I do my best to not kink the wire, but sometimes, you know, it happens. So do your best anyway. Now people do this different ways. People use drill chucks and all kinds of different ways to do this, but to be honest, it doesn't take very long, and you know, use whatever method you prefer, but it seems to work okay for me. So that's how I produce the trifilar winding, and I'm going to now wind it on the toroid. So here it is, and yeah, it's probably going to be too long. Got a bit carried away there, and that's all right. And what I may have to do is just chop it off, because trying to thread that through, especially when you've got a few turns on, is going to be difficult. So probably I'll have to sacrifice one end just to actually get it through, but so be it. So here we go. So that's the one end has gone through. So that constitutes 3 turns. Remember, every time the wire, or wires in our case, passes through the centre of the toroid, that counts as 1 turn. So that's actually 1, 2, 3 turns. And you'll see what I did is I just cut the end off that there, just to make it easier to poke it through. And that will be plenty on there. So I'll see you on the other side when I've finished winding. So I've tidied this up a bit and separated the leads now. so I know which bit's going where. So I'm going to be looking at this T1. So you see the top gold lead goes to the local oscillator, and the bottom gold lead goes to earth. So that will be these. That's the top one and the bottom one. And then this is what's really helpful, to have different coloured wires. If you look at the phasing, the top red lead goes over to the top point of the 12 o'clock, if you like, of the diode bridge. And the bottom green, so the top red goes to the 12 o'clock, the bottom green winding goes to the 6 o'clock point on the diode bridge. So that I've kind of indicated that. So that's the top red, which is going to the 12 o'clock, and that's the bottom green. It's hard to see the colours now, you can just about see it. It's going to the 6 o'clock. Now that only leaves the other two windings, which are the bottom red and the top green. And they are joined together and they both go to ground. Now it's possible to put a trim pot in there and to try and get a bit better balance and to null out the carrier. And people have done that quite successfully. Pete Juliano does that very often in his designs. This one follows a kind of simpler design, really, by Charlie Morris, which and he tried the trim pot, but he found he didn't need it, and he actually got better results without it. And certainly I've done it both ways, and so I thought I would try it at least this time without the trim pot. We can always put one in if necessary. But yeah, so essentially, so that's the bottom red joins to the top green and they get grounded. So these are the ones I've got coming out to the right. So that's the bottom red, which is this one here, and that's the top green. So what I'm going to do is we'll join those together. But first of all, what I will do, obviously those leads are far too long, but I will just chop them down a bit, scrape the enamel off the ends, tin them, and then just have a look what it looks like on the peak LCR meter. Yeah, and so here it is. Now, it's absolutely sod's law, isn't it? I mean, I've made a number of these, and they've gone fine. And the one time, when you're making a video about it, a wire snaps. As you can see here, I've had to do a little bit of repair work here, and that red wire. And that's probably over twisting it, which will weaken the wire. Yeah, so I paid the consequence for that. But yeah, so I managed to join that on, so it's not too bad. Tested it for continuity, which is fine, just with a multimeter, and then put the Peak Atlas LCR 45 LCR meter on it, just to see. It's measuring about 40 ohms impedance across all the windings. So I was thinking it would be a little bit higher than that, but that's probably going to be okay. Once those leads are a bit shorter and it's in circuit as well, we will see. Now I've just soldered together those two wires that are going to join and go to ground. So that's the bottom red and the top green. And actually tested it again, and the inductance actually goes up slightly, and so does the impedance. So we're up to about 43 ohms now, which is not too bad. I mean, I'm assuming that I'm supposed to be seeing 50 ohms. I will run with that because we're going to do a few other things with this mixer to try and ensure that the signal coming into it will see 50 ohms as well. So there are some other things that we can do. But for now, yeah, that's fine. And so I will make another one. And I've just replicated the entire same process and produced this transformer on the right, which will be T2, which is the same, it's just kind of in reverse. So yeah, so that's the transformers done. Well, the next step is the diode ring, and for that, of course, we need some diodes. And so this is what I'm using. These are 1N5711 Schottky diodes, which seem to be the diode of choice of folks that have built a few of these. So got quite a low forward voltage, which is good because you're not losing too much signal then in your mixer over those diodes. And now they are matched, and there's different ways you can do this. Alan Wolke's got an excellent video which I will link to, which talks about some of the, I think about 4 different ways he puts down there about how you can match them. One of the simplest ones being using the diode function on your multimeter. The only issue with that is it sends a very, very low current through them, and it depends on the current that you're going to be using the diodes in, and you might be using them at a higher current than that, and in which case they might not perform in exactly the same way and might not be as well matched at the current that you want to use them at. So what I did is I used the system that Charlie Morris uses, which Alan also talks about, which is you set up a simple little circuit with a variable voltage supply and a couple of resistors and a digital multimeter and your diode, and you tweak the system so that you get a specific amount of current that you want going through that circuit. So in my case, 1 milliamp. And then you test all your diodes. So I got a great big bag of diodes. I don't know whether 50, 100 diodes or whatever. And you put them all through this, and then you group them according to their readings, rather like the way that I did. If you've seen the video I made on the crystal filters, the way I did that. So you have a big sheet of paper with lots of numbers written on, and you group them together. And that's what I did. Now, I would have shown you this in action, except that I grouped this particular group of diodes a long while ago. And when I did that exercise, I grouped them all together because I knew in the future I would need a group of matched Schottky diodes for a mixer. But I will link to Alan's video and to Charlie Morris's video as well, so you can see exactly how he did it and how I did it. So these are matched as best as I can to 1 milliamps of current, which should be plenty really in terms of what's going to be going through this mixer. So what I'll do now is build my diode ring. Welcome back to the bench, and I thought what I was going to do this time actually is go back to a more traditional Manhattan style construction. So I'm not going to get the Dremel out today. So usual thing, so single-sided FR4 copper clad board. Go over it thoroughly with very fine wire wool and just then give it a quick clean and polish. Go over it with a multimeter, make sure it's nice and very, very low resistance, good continuity, good electrical connection throughout the whole of it, which is good. You don't have any dead spots or anything. And what I'm going to use, these Me pads, they're called. So I get these from, they're getting a lot of publicity this time on the GQRP Club, from Club Sales, from Graham, thank you. But you can buy them online, just search for Me pads, Me squares, I think they're called, by Rex. And they're great because you can just snap them off into whatever configurations you want, singly or collectively, and glue them on. And if you haven't got a lot of connections, they can be quite handy. Now, the reason I'm going to use it is because I'm going to build this mixer, but then I'm going to, further down the track, add other bits to this board. There'll probably be a pi attenuator on the local oscillator port. There will almost certainly be a diplexer on the IF port. I'm not going to do that today, so I need to leave a bit of space. And actually, although the Dremel technique is brilliant, I really like it, it's not so easy to to go and engrave a board that's already populated with components, where it's easier to actually just glue a little pad on. So I thought, for consistency's sake, I'd do the whole thing like this, as there aren't that many connections. So now I've done me diode ring here. Let me just zoom in on this if you can see it. So there it is. So that's the four 1N5711s in the ring. And as you see, I did it as a separate thing, so I can kind of glue it down exactly where I want it. And so that's what I'm going to do now, and then get the transformers wired in as well. And here is, well, I was about to say the finished product, but it's clearly not finished. As I said before, it's something of a work in progress. So I've put on both the transformers, as you can see. On the left, I fitted that little SMA connector. That's the local oscillator port. And actually, what I've done, I'm going to have that SMA connector there, but this bit here, which is being bridged by a little wire at the moment, this will come out, and in all probability, I will have a little pi attenuator there just to knock the local oscillator signal down, and also to get a better 50 ohms match on that port. But for now, I'll just bridge that so it's connected. And here on the RF port, that's going to go straight in, so I'm probably not going to do anything with that. On the IF port, I've just got a little wire sticking up here at the moment. I haven't even put an RF connector on it, and that's because this is going to have a diplexer on it, built for the IF frequency of 13.3 megahertz, and I don't want to just stick a BNC connector on there now and then wish I'd moved it over here or something. So I think what I'll do is I'll test it and just work off this little sticking up lead for now, and then I'll build the diplexer on there and then worry about where I'm going to put the RF connector then. But as it is now, it's kind of finished for now, and I will be able to test it.
And indeed, we will test it, but not just yet. Because as I said at the beginning, what we're going to do first, I'm going to do a separate video of testing the mixer and show you how I do that. But not before we've made a small diversion into the diplexer. And that's going to be the next video. I'm going to give that a video of its own, because that can be more tricky, I've found. So I'm going to spend a bit of time on that. So the next video will be testing the diplexer, and then the video after that will be it all connected up together, the kind of finished mixer basically, and I'll show you how I test it, and we'll see how it performs. So thank you very much for watching, but until the next time, stay safe and look after yourselves. Bye bye.